2.1 Argand diagrams. You can represent complex numbers on an Argand diagram. The x-axis on an Argand diagram is called the real axis, and the y-axis is called the imaginary axis. And we see that over here. The complex number z equals x plus iy is represented on the diagram by the point P with coordinates x, y. And x and y are Cartesian coordinates. And we see this point over here, x across, y up. So z is shown over here. Example number 1, we have to show the complex numbers z1 equals minus 4 plus I, z2 equals 2 plus 3i, and z3 equals 2 minus 3i on an Argand diagram. And as we said previously, if we have a complex number z equals x plus iy on an Argand diagram, this is represented by the point P with coordinates x, y, where x and y are Cartesian coordinates. So if we consider this Argand diagram over here, and if we consider the point z1, we have minus 4i, so we have minus 4 in the x-axis, 1 in the y-axis. So here is z1, which is equal to minus 4 plus I. If we consider z2, that's 2 plus 3i, we go 2 along the real axis, 3 along the imaginary axis. You can see here we have the point z2, which is equal to 2 plus 3i. And if we consider this point z3 equals 2 minus 3i, we go 2 across the real axis, negative 3 in the imaginary axis. You can see here we have z3 equals 2 minus 3i. And what you'd notice over here is the real part of each number describes the horizontal position along the real axis. The imaginary part describes the vertical position along the imaginary axis. And if you pay particular attention to z2 equals 2 plus 3i and z3 equals 2 minus 3i, you can see over here these are complex conjugates, and on an Argand diagram, complex conjugate pairs are symmetrical about the real axis. Of course, the real part is the same. Complex numbers can also be represented as vectors on the Argand diagram. The complex number z equals x plus iy can be represented as the vector xy on an Argand diagram. You can add or subtract complex numbers on an Argand diagram by adding or subtracting their corresponding vectors. Example number 2, we have z1 which is equal to 4 plus I, z2 which is equal to 3 plus 3i, and we have to show z1, z2 and z1 plus z2 on an Argand diagram. So first of all, if we show z1, 4 across, 1 up, you can see z1, that goes over here. So if we were to show this as a vector, we have here Z1. And if we show Z2, where we have 3 plus 3i, 3 across the real axis, 3 up the imaginary axis, you can see here we have Z2, and if we were to show this, here we have Z2. Now when we come to show Z1 plus Z2, you can think of this as adding two vectors together. So, using vector addition to find Z1 plus Z2, if we were to do that, Z1 plus Z2, we have Z1, 4i, so we have the vector 4, 1, plus Z2, that's 3 plus 3i, so the vector is 3, 3, and adding these together, 4 plus 3, that's 7, 1 plus 3, that's 4. So Z1 plus Z2 is equal to 7, 4. And if we go back to our Argand diagram, 7 across 4 up, let's show this. So we have 1, 2, 3, 4, 5, 6, 7 across the real axis, 4 up the imaginary axis. Here we have the Z1 plus Z2. And this makes a lot of sense. We have Z1 plus this vector over here. Using vector addition, we have Z1, and then from Z1 we're going to go 3 across and then 3 up. So effectively, this is what we're doing. And similarly, if we were to start at Z2 and then go 4 across and 1 up, we would end up at this point over here. So you can see, using vector addition, we can show the sums of complex numbers. Example number 3, we have Z1 which is equal to 2 plus 5i, Z2 which is equal to 4 plus 2i, and we have to show Z1, Z2 and Z1 minus Z2 on an Argand diagram. Well, let's show first of all Z1. We have 2 across 5 up, so we go 2 along the real axis, and then we go 5 up the imaginary axis. So you can see here we have the vector Z1. So let's just draw this on. We have here Z1 which is equal to 2 plus 5i. Z2, that's 4 across and 2 up. So if we were to show this on an Argand diagram, we go 4 across the real axis, 2 up the imaginary axis. Here we have Z2. And this is equal to 4 plus 2i. And we need to show the vector Z1 minus Z2. So, if we were to do that, first of all, let's work out Z1 minus Z2. Z1 minus Z2, we have over here Z1 as a vector, we have 2, 5, minus Z2 as a vector, 4, 2. So here we can have 2 minus 4, which is minus 2. 5 minus 2, that's 3. So the vector z1 minus z2, that's minus 2 along the real axis, 3 up the imaginary axis. Here we have, if we draw this on, we have here z1 minus z2. And just for benefit, we can write this as minus 2 plus 3i. And that makes a lot of sense. We're at z1, and then we want to go from z1 minus z2. So you can see here, z2, that's 4 across, 2 up. So the opposite of that, minus z2. You can see here, we go 4 to the left and 2 down. So if we show this, you can see here we have minus z2 as shown here. And this will equal minus 4 minus 2i.